So suppose that G is a group, then its center, Z of G are all the elements of G which that I should say, that commute with all of G. So suppose that this is G, and there are there's of course the identity, but there are other elements such that these elements they commute with all the elements of G. So they're called the center, this set. So in other words, if A is in the center of the group G, if A times G is equal to G times A for all G in big G. Okay. So now the interesting thing is that Z of G is also a group, because all the elements here are commute with all the elements in G. That means all the elements of ZG commute. Therefore, ZG is an abelian group. And to show that, let's just do one little thing. So if A is in Z of G, that means, of course, that A times G for arbitrary G is GA. Now, if I multiply it by A inverse of A of G is A inverse G of A. But the left-hand side is so the left-hand side is G, and the right-hand side is A inverse G of A. And of course, this means that if I multiply by A inverse GA inverse is A inverse of G. Therefore, A inverse is also in the center of G. Okay, so what we have shown is that if A is in the center of G, then A inverse is also in the center of G. And this is just one of the axioms that one of the postulate I've just shown satisfies. You can show the other ones, they're very easy. Okay.
Sorry, you said ZG is an abelian group.
Yeah.
But you only showed that it commutes with the center, but there are other elements with which G doesn't commute. So wouldn't that matter?
I mean, Z of G consists of all the elements which commute with everyone. Oh. So they must commute amongst themselves, right?
Okay, I get it.
Yeah, okay, good. Okay, so I made another comment, and which is something that was picked up by Okono. And the comment was that, since Z of G is a normal subgroup, because it's abelian, right? So it must be normal. It's a normal because it's abelian in a normal subgroup. That means that G over Z of G is a quotient group. Okay. And this quotient group, it can be shown by using a theorem that we will prove in the next week, I think, so this G over Z of G can be shown to be isomorphic to what is known as the inner automorphism group of G. Okay, so what is an inner automorphism? It involves a certain action which we will actually define today. So when we when we go and discuss the theorem, and we will come back to this. Okay, so I want to now move on to some definitions, unless you have some questions. We have a comment in the chat. Okay, yeah. Z is a subset of G, yes. Right, safe. Okay, any questions? Any more questions or comments? All right, so in that case, let's define the direct product of groups. So this is a definition. So this is a very useful idea, the direct product of groups, because often we actually deal with multiple groups, the action of multiple groups on a mathematical or physical system. So if we have two groups, say G1 and G2, then we can define the direct product or the direct product group, which is denoted by G1 cross of G2 with the multiplication given by, so suppose that G1 and G2 are two ordered elements of G1 of this group, right? Is this clear what this notation means? So I'm taking some element G1 from big G1 and some element G2 from big G2. And this is an ordered double, or an ordered pair. Okay, so this times, say, G1 prime and G2 prime. So these are also elements from G1 and G2. So the product is obviously defined by G1 prime, G2 prime. Okay. So under this multiplication, we define a new group, which is called the direct product group. Okay, is the definition clear? So you have to verify that this is actually a group, right? And it should be very clear that this is a group, because there is no kind of quote unquote interaction between the two guys, right? They're, okay. So the group G1 is isomorphic to the subgroup, which consists of G1 from the first group and the identity element from the second group, right? Maybe I should write this. Okay, so this is isomorphic And G2 is isomorphic to the identity, the element from the, yeah, I'm not sure if this is the way to write it. No, yeah, I don't think it needs brackets here. Yeah, so this is E2, E1, G2. Okay? So these form normal subgroups of G1 cross G2. Okay? Now, there is another subgroup which is not a normal subgroup. So if the product group or the direct product group happens to have the same factors. So if you have G cross G, then all the elements of the form where you take the same element from both groups, all these elements form a subgroup which is isomorphic to G, called the diagonal group. Okay, the diagonal subgroup G of G cross G. So this is different from, say, the G, which consists of, say, the identity element from the first group and all the elements from the second group, or G, which consists of all the elements from the first group and the identity element from the second group. So this is different. So the diagonal subgroup is not a normal subgroup. Okay? So even such a trivial construction, seemingly trivial construction, has some interesting structure in it. Okay? And
Sir, I didn't quite get the comment 1 and comment 2 clearly. Would you please explain?
Okay. So comment 1 is that if I just take the identity element, say from the second group, and then this multiplication also forms a group where this guy is just E2, right? This guy is E2, sorry. So this is just E2, right? This is a closed operation and it satisfies all the group theory conditions. And these groups are isomorphic to, say, G1 and G2, and they're normal subgroups, almost trivially so. Right? They are, yes. But if the two groups, G1 and G2, in the direct product group, if both of them is the same group, then we have this option where we pick the same element from both groups. And then we impose this multiplication rule on that. Right? So if you restrict to these forms of elements, then we get a group which is isomorphic to G, but its it's a subgroup of G cross G, and it's called a diagonal subgroup. But this group is different from either this left G or right G. Let's call it, this is R, this is left, the left copy and the right copy. And you can also show that this is not a normal subgroup. Okay.
So this diagonal subgroup is like on the matrix 1, 1, 1, 2 thing. Only the 1, 1, 2, 2, 3, 3 this part exists.
No, it's because it's, so if you think of matrix groups, these are actually direct product of matrices.
So I think the representations of what Fahan is saying might be like that. Would it be?
No, because your representations are, so yeah, the representation will be something like this. So if you, a matrix of the group would be M1 cross M2. This is not matrix multiplication, okay? This is the direct product. And elements of G cross G of the diagonal G of say G cross G, they would be of the form where it's M1 cross M1. Clearly, you know, this matrix is not a diagonal matrix because they don't have to be.